Hello, here we continue looking into properties of operations on matrices. And we have two defined: addition and multiplication. And for addition, it works for a pair of matrices of the same size. So we'll introduce notation for the set of all matrices with m rows and m columns and real coefficients. And then the sum, calling it C, is going to be the same size with m rows and m columns. And the way we computed this was to look at two linear maps transforming n vectors into m vectors, say f and g, each of them given by the corresponding matrix. Then we had the notion of adding maps, and the matrix of that linear result is the sum of matrices. So the answer for the matrix entries of matrix C, something sitting in ith row in j's column, will be just the sum of corresponding matrix elements of A and B. That is a generic recipe of adding two matrices. We just align the tables and sum up their entries. More interesting to implement is multiplication. It works again for a pair of matrices. This time they should be aligned in a different way, not by sitting in the same set of matrices, not just having the same size, but having the same numbers for columns of the first and rows of the second. And then the result, which is called the product of the two, is a matrix of size L by n. Let's call it C again, and then the generic answer for its matrix entry is as follows. We take elements in the ith row of the first matrix A and multiply them by corresponding elements in the jth column. And take the sum of all these products. So that sum makes sense exactly because of this restriction that the number of elements in any row, the number of columns, is the same as the number of elements in any column of the second. So that is the definition, if you like, of matrix product, but that was coming from a composition of this time two linear maps following one each other. So matrix B was the matrix of linear map F, and matrix A is a matrix of linear map G, and then the composite of these two linear maps is linear again, and its matrix is C. And that origin of matrix operations is the easiest way to see what are the properties of the two when they are combined. So for example, if we take a matrix A and multiply it by a sum of two, that would mean that matrix A has, say, L rows and M columns, but then both B and C will be of the same size, M by N. Then the result will be the same as if we distribute A through the sum. That will be the sum of two products. And that is simply because in terms of maps, which are given by those matrices, we have the following situation. So we have one map, I'll call it F, which will have matrix A, and then two maps, G and H, are starting at the same place, ending at the same place, which will have matrices B and C correspondingly. And then we are composing this matrix multiplication corresponds to computing composition of two possible successive maps, G with F and H with F. And then the results are, of course, the sum. That is just by our definition of the sum of maps. Similarly, we have different distributivity law if we take two matrices of the same size and compute their sum, and then if we take the third, which is multipliable with the sum, that would be, if we have, say, these dimensions, then the result can be computed in a different way as a sum of two products. And this time we have a different situation, but similar to the one before. We have one map followed by the two, and if, say, this is H with matrix C, and these are F and G with matrices A and B correspondingly, then again, computing the sum and composing it with H is the same as computing the sum of two composites. So in special case, when we have square matrices, that will be the short notation for the set of matrices of size n by n. We have both addition and multiplication. And these two operations of addition and multiplication satisfy usual arithmetic of numbers. Well, I didn't say anything about just addition, but addition, of course, is commutative and associative and has a special matrix 0, which will be just a matrix full of zeros, which when we add it to any other matrix doesn't change the second summand. And for multiplication, we have these properties with respect to addition, and also we have associativity property, which I will squeeze in here, so we can compute the triple product of three matrices in two different ways. And that will just correspond to looking at the sequence of three maps which can be composed and computing the composition in two different ways, and of course the result is the same. So for the set of square matrices, we have a situation similar to numbers. We have two operations on those matrices, addition and multiplication, satisfying usual laws, and that is making the set of matrices a generalization of numbers. But there are new phenomena for these operations, namely for multiplication. With respect to numbers. So if matrix is of size 1, the smallest possible value for the size, then we're just looking at numbers effectively. A matrix of size 1 is just one entry, it's a number, and then addition and multiplication are just operational numbers. But if we have size bigger than 1, say 2, already we will have several new features which are not seen in numbers. So for example, the product of matrices is no longer commutative. We can find a pair of matrices, say size 2, and then we can make them such that their products computed in different order will not be the same. So for A, we can take this 2 by 2 matrix, for B this. Then computing this product, the result of course is 2 by 2, so we have to compute 4 entries. The first one is when we take the first row from the first matrix and the first column from the second and align the components and multiply and take the sum. So 0 by 1, 1 by 0 will give us 0. This entry comes by this formula as the sum of products of components of the first row and the second column. Second column is full of zeros, so we'll have 0 here as well. And then the second row, starting looking at these two entries, we'll have to use the second row of the first matrix. Again, it is full of zeros, and it will be just total 0 as a result. But if we take these matrices in the opposite order and multiply them, the result will not be 0. So this entry will have 1 times 0, 0 times 0, total 0. This entry will be again coming from the product of that row, which is 0 with any column, 0 here, but here we will not have 0 because 1 times 1 0 and 1 0 multiplied and summed up will give us 1. So that is perhaps the easiest example of non-commuting pair of matrices. Continuing with weirdness, if we just take one of them, say A, and multiply with itself, the result will be again total 0, because okay, if we compute this entry, we multiply this row by that column is full of zeros, so the result is 0. If we compute this entry, we take this row, it is full of zeros. If we compute this entry as well, we take the second row of the matrix, it is full of zeros. And here it also is 0, because even if the row is non-zero and the column is non-zero, but the matching makes it all 0. So the square of a non-zero matrix is total 0, is the 0 matrix, which is impossible in numbers. If we take a non-zero number and multiply it with itself, it is never 0. If we take the other one in our example here and compute its square, the result will also be unusual, but more subtle. So if we do the computations, here we'll have 0 because of that 0 line, and so isn't here. Here we have 0 because of that 0 column, and here we'll have 1 0 1 0 giving us 1. So the square of the matrix B is the same matrix B. In numbers we have solutions of this equation, but they are either 0 or 1. This matrix is neither 0 nor 1. The identity matrix for the size 2 will be this one. So this is something new, and that complicates algebra of matrices, making computations with matrices, but not that much, because majority of expected properties are still there.